Alright, so hello everyone, and welcome back to the channel. Today's topic is one that I had a lot of fun with, and it's how to do 3D projections into a 2D space from scratch. So today what we're going to do is we're going to actually take 3D points and project them into 2D, and we're going to do some nice rotations as well, as you'll see off to the side here. And what we're going to do is we're going to do this without using any real external libraries. So we're going to have Skia for sure, and we're going to use Skia path and a couple of shared values, but we're not going to use any kind of external libraries to rotate things or anything like that. We're going to do all the math on our own. So before we get started, the next thing I want to do is shout out a few different creators, and I'm going to put their different monikers off to the side just so people can see who they are. Basically, while I was doing the research for this, I had to watch a ton of different videos, and I also had to read a whole bunch of different blog articles and things like that. And so this video is basically a culmination of a whole bunch of research that I ended up having to do. So the problem that I had was that one person might handle the projection, but then not how to bring it back into the actual screen. And then someone else might do rotation, but then after that, they wouldn't actually code anything. Or some people would do the projection, then they wouldn't do rotations, and so on and so forth. Basically, every single video that I watched was missing kind of one piece of this. So what I've tried to do is basically take everything that I learned from all these different creators and put it together into one coherent video that we could use in the React Native world. So before we get started, one other thing I want to say is that if what you're doing is just putting something into production and you need it done quick and you need it done correctly, the best way to do this is just to use Process Transform 3D from React Native Skia. You don't need to sit through and do all this different math stuff. This video is really for math enthusiasts who really want to learn basically how this whole thing works, and they want to kind of do it for fun. This is not necessarily you do something in production, just because Skia already has a lot of this stuff built in. Okay, so as always guys, the links to the code for this project are down in the description. What I'm also going to do is link to all the different videos and blogs that I use to research down in the description so that you can have the full picture of everything that it took in order to build this entire lesson and this entire project, and you can reference any of these materials at any given time. All right, let's get into it. All right, guys, so as I said earlier, the first part of this is actually just going to be the mathematical and conceptual basis behind things. The reason being, if you don't know how the mental model of this works, it really makes no sense when you program it. And the other reason too is that I'm going to be referring back to these diagrams and this information kind of as we go throughout the coding anyway. So I thought it would be good to kind of give this to you first so that when we get into the coding, I can look back and say, here's how we did things. Okay, so the first thing that we want to do here is actually go about creating a projection matrix. So what a projection matrix does is, given a set of points x, y, and z, it gives us back the information that we need in order to map the 3D coordinates that we have into a set of 2D coordinates that are equivalent on a 2D surface. Before I get too into how we actually build up this projection matrix, I want to first give a little bit of background about how matrix multiplication works, just because I know a lot of people here might not be familiar with it, and I felt like it might be useful to get everyone on the same page. So matrix multiplication really isn't that complicated. But it is very common here. So let's say we have our points x, y, and z, and we just want to preserve them. So what you can do is kind of build your matrix here in this sort of like staircase type pattern, where the ones sort of match what you want to multiply by. So how this works basically ends up being that the first thing gets multiplied by the first in this vector, the second item gets multiplied by the second in this vector, the third. Then when you start getting into other rows, you just sort of repeat this sequence where you multiply by the first, second, third item, and so on and so forth. So if I was to sort of break this out and expand a little, what you would see is x, it would be x times 1 plus y times 0 plus z times 0. And then you would have x times 0 plus y times 1 plus z times 0. Finally, you'd have x times 0 plus y times 0 plus z times 1. And you can see here pretty clearly, just based on the fact that everything else is multiplied by 0 except these, you would get back basically the exact same values in your matrix of x, y, and z. So really, when we work with matrices, the most important values to modify x, y, and z are these ones. Of course, you can see that because of the addition, like the other parts of the matrix have important roles as well, and they will also get integrated into this when you do the multiplication. But these three are kind of the core focus of what we're going to do most of today. Okay, so the next thing I want to do here is talk a little bit about what things look like from the perspective of our application. So let me draw a couple of lines, and I just need a couple more here. And then one big one back here. Okay, so you see how what we have here is this area where we have this line on this side and this line on this side, and they're kind of spanning out this way, right? This is called our field of view, which is often just abbreviated as FOV. And this field of view is kind of like how your eyes see, right? They sort of, they can see through your peripheral vision, left and right, and you sort of have this distance through the center. So things work a little more complex than that when it comes to how we model this in terms of 3D graphics. So here is where you have you, which is also called the camera. Oops. And what we do is we also have these other sort of key points. This one is called the near plane. And this is basically like your computer monitor here. So the distance from the camera to your computer monitor is this. Also, you have the far plane, which is about as far back as the application is going to just draw things, basically. Now, something interesting happens if we take this and we sort of divide it in half. And some people will see it right away, some people won't, somewhat because of my bad drawing skills. But actually what we have here is two right angle triangles. And this distance between the left and the right part of the far plane has an angle that we can call theta. So interestingly enough, we have the adjacent here, like you would have in a right triangle, and we also have the opposite. So if you remember from trigonometry, we have our SOHCAHTOA, and depending on which sides you're given, you can kind of determine the ratio for the other ones. And because we have opposite and adjacent, we can of course use tan here. So what we're going to do is use tan as a scaling factor in order to take any of our points and sort of reposition them as we go. So we can say that so far we have this tan with theta divided by 2, and it's theta divided by 2 because of course this angle here is kind of cut in half, so we have two right angle triangles. However, there's kind of a problem here. Let's say we had a box, right? And let's say that this angle got narrower. Let's make that there. And let's put this here. So if we had a narrower angle, we would want our box here to actually take up more of the field of view. So if you have a bigger field of view, your item is smaller. If you have a smaller field of view, your item should be bigger. And if we just use tan, you'd kind of get the opposite effect. So what we have to do is we have to actually take the inverse, and this will allow us to sort of scale tan properly. Sorry, scale our values, our points properly within this model. So now that we know that we have 1/10 as what we want to use to scale our points, we actually can use them for X and Y. So the way this is going to work is that in the top right-hand corner of our matrix, which as you remember is the X part, we are going to use the aspect ratio, which is width over height, and multiply that by 1/tan theta divided by 2. And then we're going to have 0, 0. And then for Y, we're going to do 1/tan theta divided by 2 and 0. And then in the last row here, we need to do something about Z. Okay, so now As you recall, we're looking for what we're going to do with our z coordinate. And if you remember, we have these different parts of our model, one being the near plane and one being the far plane. And one interesting one too that we didn't talk about yet is this line straight down the middle. So this line down the middle is actually the z-axis. And the near plane here can actually count as our x or our y-axis. It just depends on the angle that you look at it from. From up top, it's x. From off to the side, it's y. But at the end of the day, this model holds no matter which angle you're kind of looking at this at. So the question is, how do we adjust for sort of this space here to be able to map our coordinates within that, and also kind of like build in this space here? So the way it's going to work for the top space is that we're going to say our z far gets divided by our z far minus z near. And then for the inner space, what we do is we say z near times z far over z far minus z near. Okay, so at this point, if we go back to our main matrix and then we apply our stuff from the last section, so we do z far over z far minus z near. Interestingly enough, we kind of run out of space, right? So to incorporate our x, y, and z. And the reason that happens is because when you do translations, they're a type of transformation that's kind of special, and they don't necessarily maintain their center point. So you actually need to increase this to a 4-dimensional matrix in order to have the information map back to x and y. And the way that that works is, I'll show this really quickly. We have to have our z far multiplied by our z near, and again do our division. We can kind of just fill everything with zeros here. And then for the 4-dimensional part, it's pretty simple. All you do is you just make this 0, 0, 0, 1. And how this is going to work is that now we'll have x, y, and z be variable. So these we actually specify. And we're going to have a 1 at the bottom, which is most of the time actually it's just called w. And so what's going to happen is when we multiply this through, we're going to be able to divide x by w and y by w in order to get a value that we can map back to a 2D space. Okay, so the last step to this, once you've multiplied your point by the projection matrix, what you have to then do is do some final operations using w in order to take the x, y, and z and push those back into x, y coordinates that you can actually use on the 2D plane. So what we're going to do is we're going to create a temporary x, and we're going to say that this is x divided by w, and then we're going to have a temporary y, and that's going to be equal to y divide w, and then the final version of x that we're going to actually use to project back is going to be the temporary x plus 1 divided by 2 times the width of our canvas. And then to get the final y that we're actually going to use, we're going to do 1 minus the temporary y plus 1 divided by 2 times the height of our viewport. And so that's basically everything you need to know in terms of the conceptual mathematical part. Let's go now and do the coding aspect of this. The first thing that we're going to do is just look into our boilerplate. It's a light boilerplate. There's not a lot of stuff here. I just wanted to get us started so that we don't get bogged down in little details. Also, I'm sure people are going to wonder how and why I have my device off to the side here. I'm using Radon IDE from Software Mansion. They do not pay me or sponsor me for this. I just think it's a really great tool, and I think you guys should use it too. Go to the Software Mansion website for Radon and check it out. I'll be using it throughout the course of this demonstration. Okay, so in our boilerplate, I just have a couple basic types, just a 2D coordinate type and a 3D coordinate type. I have some phase coordinates here, which are just the X, Y, and Z position of the different points that we're going to use. So naturally, people are going to wonder why these are points with values between 0 and 1. It would seem more natural to give points that were actually points on the canvas here, like, I don't know, 300 and 200 or whatever else. And the reason that we don't do that is because the algorithms here assume that you give points that are neutral or sort of agnostic towards the canvas you put them on. So what happens is our algorithms will rotate and they will project, and it's not until that last step where we multiply by the width and the height that these points get converted back to values that can be used on the canvas. And that's really good because it means that no matter what the size of our canvas is, our points will adjust dynamically depending on that size. You'll see more about how that works in a little bit, but for now, that's about the level of depth you need to understand. And finally, I just have a really basic couple sliders here that are hooked up to shared values. These shared values are going to be used for rotations later, but for now, I just needed something to hook up to this slider thing. But as you can see, they do nothing, nothing's showing, and I just have some really basic view styles. Something I do want you to keep in mind is that the Skia canvas here is actually a square, and let me find a way to show you that. Probably I can just do this. And the reason it's a square is because of our mathematical calculations that we're doing later. It was just easier to work with a canvas that had an equal width and height than it was to work with one that had like a different height and a different width. So we're going to be going with a square canvas today as well. Okay, so as we said earlier, what we're going to do is create a method to project our 3D points into 2D. So let's do that. And we'll call it project matrix 2D. And this is going to take in some coordinates, which are of type, not that one, coords 3D. And we're going to make a worklet, because if we don't, our app's going to crash. All right, so let's take a look at our diagram here. And if you remember, we had this sort of space that went between the camera part here and the end of Z. And we get to define that constant ourselves. So we're going to call that Z distance, and it's going to be equal to 10. The next thing that we need to define is our field of view, which if you remember is this angle here that also kind of goes out to this side and to this side. Again, that's also a constant we get to define. So we're going to call it field of view. And that's going to be equal to math.pi divided by 6. And this is just because it looks nice. This is just a nice angle in radians that I picked. Okay, so we're also going to want to define the near plane and the far plane. And if you remember from our diagram, the far plane is this line here. So the far plane is going to be equal to the Z distance times 5, because I'm going to get it to extend a little further back. And the near distance is going to be the Z distance divided by 5. And that should give us some good numbers that we can work with here. So the next thing we're going to do is create this matrix here. And we're going to obviously have to plug in these different functions. And the only thing that we're really missing right now is this kind of 1 over 10. So let's create that really quick. So we're going to say const f equals 1 divided by math.10, and using the field of view divided by 2. Okay, so in our diagram, let's create this vector here, which has all of our points. And so we're going to call that vector 4 for 4D vector. It's going to have an x value, which is going to be the coords.x. It's going to have a y value, which is going to be coords.y. Oops. It's going to have a z value, which is coords.z. And And as you saw in the diagram earlier, we're going to have a w, which we're going to make just equal to 1. And let me push that up a bit. Okay, so now let's actually put these functions in the matrix. And actually really quickly, I'm going to create another variable and call it AR for aspect ratio. And in our case, this is just going to be 1 because we're using a square. But if you were doing this on your own side, you probably want to have height there. So I just wanted to include that just for convenience sake. Okay, so let's build this matrix out now, which is pretty simple to do. So we just say const projection matrix, or PM, is a 2D array of numbers. In the first one, we're going to have the field of view times the aspect ratio, and we're going to pad it with zeros. Next, we're going to have 0 with the field that we did earlier and pad with zeros. Finally, we're going to have 0, 0, and then we have to plug in these functions here. So let's do that. So far divided by far, sorry, it's probably z far, I think. No, I just called it far, okay. Far minus near. And then for the other one, we have negative far times near. And we divide it by far minus near. And for this last one, we have 0, 0, whoops, 1, 0. Okay, so the next thing we're going to do here is we're going to actually multiply out these matrices. So we're going to say our result is going to be equal to x. And we're going to do v4.x times the projection matrix at 0 at 0 at 0 plus the matrix dot y times 0, 1 plus, and this gets pretty repetitive, so I'm just going to probably just copy these, 0, 2, and then we do the same for 0, 3. Okay, and there's a nice pattern here. Basically, this will occur for x, y, and z, and w. And basically, all we do is we go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and that will multiply every row by every column. Okay, so the next thing that we have to do is we have to actually do some division to get things back to 2D. So we're going to say temp x is equal to result.x divided by result.y, .w. And we're going to do the same thing with y. And then finally, we're going to return a 2D coordinate set where x is going to be equal to temp x plus 1 divided by 2 times width. And y, we're going to do something similar. For y, we're going to do 1 minus temp y plus 1 and divide that by 2. So now if you were doing this with a different width and height, you would just swap that one out for height. But basically this is exactly what you need. All right, guys, so I was quickly looking back over this and I realized I made a big copy pasting goof. So in the multiplication, it has to be x, y, and then this row has to be z, and then this last row has to be w. Okay, so when you do the multiplication, everything else was right here, but it has to be x, y, z, w. Okay, that's fixed now. Let's move on to drawing the path. So to draw the path, what we need to do is start by creating a hook. It's going to be path is use path value, and that takes in a fresh path. And of course, we have to make this function a worklet. So inside of here, we need a 2 for loop array because our face coordinates array is a double array. So let's do that. We're going to say for const face coordinate array of face coordinates, and And inside there, we're going to say for const index and face coordinates of face coordinates array dot entries. And inside here, we're going to do our projection. So we're going to say project matrix 2D. And we're going to do we're going to put our face coordinates in there. And then after that, we are going to say if index is equal to 0, we are going to move to the new coordinates dot x and the new coordinates dot y. Otherwise, we're going to do a line 2. And then we're going to close the path. And finally, we are going to just return the new path. Okay, so this isn't quite going to work, but I'll show you why in a second. First, I'm going to put in the path component. So we're going to say here that the path is equal to the path. The style is going to be the stroke style. The color is going to be terminal green. And the stroke width is going to be the line width. And as you can see, we have an X. Like, what the hell is this, right? And the reason this happens is because you actually have to push the cube back, because the cube right now is, if you see the near plane, it's just like pushed right up against the near plane. So it looks super weird. And the way we fix that is pretty easy. All we have to do is in our coordinates, we take the Z and we push it back just a little bit. Oh, why doesn't it like that? Oh, because it's an object. It's not an array. And there we go. And as you can see, we have our nice cube projected. The next thing that we're going to do is we're going to rotate this thing around. Okay, so now that we know how to project 3D points into a 2D space, the next thing that we want to do is learn how to rotate. And the reason is because rotating is just fun. It makes graphics interesting because it allows them to move. And it's just really interesting to learn in general. So what I'm going to do is I'm going to show how rotations work in 2D. The reason is because once you get to 3D, the calculations that you have to do on paper become really long and really tedious, and they would take just too much time to comfortably show in a video, and more time than would kind of make sense. So what you can do is you can take these principles that we learned from 2D, and you can kind of assume that they apply in 3D because they work in similar ways. Okay, so let's start off with a square, since we're doing things in 2D. And let's say we have a point 3,3. And then we have another point, which is -3, 3. And then another point, which is -3, -3. And then a final point, which is +3, -3. And then we draw our nice little square. So what we want to do is take this square and rotate it in this direction. So now in order to rotate, what we need is a rotation matrix. Rotation matrices generally use sine and cosine to be able to get us to rotate around any given point. Generally what happens is that our points kind of have this fixed spot in the middle, and we use that to rotate. What you'll notice here too is that we don't have to move into an extra dimension in order to do these transformations. That's because rotations will always maintain their center point nicely. So let me quickly write out our rotation matrix. And what we're going to be using today is cosine theta negative sine theta. And then we're going to have sine theta. And then we're going to have positive cosine theta. And what we're going to do is we're going to take each of these points here, and we're going to multiply them by this. And what I'm going to do is I'm just going to make theta equal to an arbitrary value. You can make this equal to anything, but I find 1.1 gives it a decent rotation. So what I'm going to do is I'm going to go away and I'm going to pre-calculate the values of sine and cosine. And then I'm going to kind of get things started so that we can do all the matrix multiplication. So as you can see here, I've kind of set this up already for us. I pre-calculated our sine and cosine so that we have that matrix all of these times. As you can see, the values don't actually change in this first matrix. That's because sine and cosine multiplied by a certain angle will always be the same. And in the other column here, I have our points that we want to do matrix multiplication on. So I'll do a couple of these and expand them out, and then what I'll do is I'll sort of do the rest of them for you. But just so that you get a feel for matrix multiplication, I kind of wanted to show this one. So the first thing you do is you take the first item multiplied by the first item here. So 0.453 times 3. And then the next one's going to be negative because the 0.89 is a minus. So what we're going to do is subtract that from this value times this value. So 0.891 times 3. And we'll do the same thing down here. So 0.891 times 3. But this time we're going to do plus, because this is a positive number, 0.453 times 3. And what we'll do is we will take the final result of that, and that will be negative 1.314, and then 4.032. Let's repeat the same process for the next matrix, just so we can get a feel for how this works. So we're going to have 0.453 times negative 3. And that's going to be minus 0.891 times 3. And next thing we're going to do is 0.891, which is this, multiplied by that, negative 3. And this time we're going to add it. So we're going to say 0.453 multiplied by 3. And when we add all this together, what we get is negative 4.032. And then you get 1.314. Actually, that's negative as well. Okay, so what I've done here is I've multiplied out the last of our values. Let's plug these into the chart and let's make sure they actually did rotate. So we'll do negative 1, positive 4, negative 1, positive 4. And the next point we have is negative 4, negative 1. So we need a negative 4 and a negative 1. Next we have positive 1, negative 4. So there's positive 1. And we need negative 4, which is down here. And then what's our last point? We have positive 4, positive 1. So positive 4, positive 1. And you can see that if I connect these points, we have another square that we successfully rotated in this direction. Okay, so for this last section, what I'm going to do is explain how the rotations work in 3D, but I'm going to do it on a high level, sort of conceptual type explanation. The reason is because you just saw the calculations we did just for 2D, and it got quite long and quite tedious. Now imagine I tried to multiply this out for 3D. It's a lot easier to show in code, and I'll do that in a minute, but I want to quickly explain kind of how all this stuff works together and the terminology. So I took all these diagrams from Wikipedia because they do a great job of kind of explaining how this works. When you rotate in 3D, there's kind of 3 axes you could take. One is pitch, one is yaw, and one is roll. Each of those directions are represented by each of these three matrices here. However, if we multiply them together, we actually get this one here that we can do everything in just one matrix, which is really great. And this is what we're going to use in code because it's kind of the easiest way to do things. So when we do this in code, alpha is going to be yaw, beta is going to be pitch, and gamma is going to be our roll. And so yeah, let's put this all together and jump into VS Code. So now that we understand how 3D rotations work conceptually, let's code it out. So we're going to call our function rotate 3D. And we can't forget to make that a worklet, otherwise the app will crash. And we're going to take in our 3D coordinates, and we're going to take in a roll, sorry, not row, pitch, and yaw. All right, so inside of here, just like I did when I was calculating things by hand, I'm going to pre-calculate the cosine and sine values. This is actually kind of an optimization because you don't want to be recalculating them every single time you want to multiply. So we're going to say const cy is going to be math dot cosine of yaw. And then we're going to do this for pitch and roll as well. So we'll call it pitch and we'll do the same thing for sines. So we'll have sine y, sine pitch, and sine roll. Oh, and then I have to make this sine. Almost made another copy paste error, but we dodged it. And what we're going to do here is we're going to return an x value, which is going to be cy times cp times x plus cy times sp times sr minus sy times cr times y plus cy times sp times cr plus sy times sr times z. Okay, so next up is y. That's going to be sy times cp times x plus sy times sp times sr plus cy times cr multiplied by y, and that's going to be added to sy times sp times cr minus cy times sr times z. Okay, so the last one up is z, which is negative sp times x plus cp times sr times y plus cp times cr times z. Okay, so let's do the fun part, which is actually making this rotate. As you can see, if I move these now, nothing's really going on. It's not that interesting. So what we're going to do is we're going to say const roll rotation is going to be equal to minus roll value dot value divided by width times math.py. And we're going to do the same thing for the pitch value. And this time it's going to be pitch value instead of roll value. So now in here, we're going to say const rotated point is going to be equal to rotate 3D. And inside here, we're going to pass the face coordinates. We're going to pass the pitch rotation. And then we're going to pass the roll rotation. And then 0 because I didn't do a yaw. And so in here, we're just going to pass the rotated point. And after a hot reload, as you can see, everything rotates really nicely, just as you'd like. All right, that's everything, guys. I hope you enjoyed this video. I hope you had a lot of fun with it. And yeah, as always, happy hacking.